Yeah, I'm doing well, Omar.
Okay. All right. So yesterday when we started the session, when we ended the session, I asked if there were, would you like to continue to do kinematics, which was describing motion, and now instead of doing dynamics, which I had planned today, the causes of motion. And emphatically, everyone decided, almost everyone emphatically chose to cover forces. And I'm glad I get to do that today, but I have to ask, are there any questions from yesterday's material? Is anybody saying anything in the chat? Yes, I'll do that at the end. So without further ado, let's get started on today's stuff. Are you? All right, let's get started. Can you see my? All right. Okay. Okay, today we're going to talk about Newton's this is going to be the first description of it, and it's going to be in everyday language. It's the first law, sometimes called the law of inertia. It says that it says objects that are in motion or rest tend to stay in motion or rest unless acted upon by a net force. And the concept of a force, it's a complicated concept. It's actually subject to different interpretations at cutting edges of physics. But for our purposes, everyday language, Elliot, can you? Zoomed out to a ridiculous extent. Okay, or is, no, this is from yesterday's.
Okay. Okay.
Yeah.
There you go. Okay. Let's do that. That might be easier as well.
Okay.
You know, it's just to go back.
Okay. All right. All right, here we go. Sorry about that, technical difficulties. I'm new to this. The second law says that force and finally, the third law says that when two objects,
Actually, hold on. Give me a second.
Yeah.
Some of them are saying can't turn on yet, so it's gonna shut. All right. Hey, can everyone hear us right now, or is there still an issue with the audio? So it seems like most people can hear us.
all right, just checking. Who again can't?
Well, I guess they wouldn't be able to hear it.
Okay.
Yeah. Okay, but it seems to be working, so just continue, and I'll try to talk to those people.
Yeah, I asked people who have no audio if they can hear me via audio. Nice. All right. So what are we looking at again? The big screen. Elliot, is everybody's audio still good? Okay, let's get back to it. When two objects are contact, with each other, they exert Third law says when two objects are in contact with each other, they exert equal but opposite forces on each other. All right. This is probably the way it's been explained. This is a popularization of the third laws. To do physics, to do well in this class, we have to be more specific. Oh, that's how you do it. We're going to go over the formulations of Newton's three laws of motion. In more precise terms. So the first law, in more precise terms, says the following. Objects that are traveling with a certain velocity v, both magnitude and direction, will continue to travel with that velocity v unless acted upon by a net external force. That sort of clarifies what we mean by in motion, because motion could mean many things. You could be accelerating, you could not be accelerating, but so we have to be more specific by what we mean in motion. And in this context, in motion means with a constant velocity. So let's move on to the second law. Yep, F equals ma. The sum of all forces equals mass times acceleration. You are correct. I think it's better, though, although this is the most popular way to write this formula, a more intuitive way to write it that actually reveals physical insight is A equals F net over M. So the harder you push something, the lighter an object is, the more it will accelerate, is what this formula is saying when acted upon by a certain push, a given push. And another way to write this is and why can I write it like this? All right. The reason I can write it like this is because if we realize we realize that A equals dv dt equals f net over m, then that means, because A is equal to dv dt, that implies that and if you move this m inside the parentheses, inside the derivative, you can do that because it is a constant. And then you define momentum P equal to mv then you will get that F net equals dp dt. Hopefully I didn't use that much calculus. You could replace the lowercase d's with capital Greek letter delta, and the same sort of argument would hold. Oh no! Oh, that's good to point out. P is in this case equal to not position, but what is it? Momentum. Which is the product of mass and velocity. But position, which is usually an S or an X or a Y or a Z or sometimes an R, that is all equal to V times T. And these are vectors. They're kind of vectors. So good seeing the difference between these two formulas. Okay, how do you scroll up? Oh, with one finger instead of your whole hand. Okay. And the third law, again, more precise. Oh, Which derivative of velocity is acceleration? Okay. Acceleration is the first derivative of velocity. How did you go from m dv dt to, I went,
I'm not sure if that's a type.
is that a typo, or do you just mean m going inside of the d?
Bottom 12, and let's see what you wrote down.
Okay, yeah, let's do that. Oh, yes, okay, sorry.
But then you can explain what you did anyways. Remember, not everyone has a chance.
Okay. So these D's are just changes. Finite changes if you've never done calculus, infinitesimal changes if you have done. So again, these are just D equals changes equals delta. So if F net equals m dv dt, I think we can all agree that is true. Then if you take the, okay, does a constant change? So what is the change of a constant? It's 0. So if you move it inside the change, quote unquote, operation, then it remains the same. I'll just do it out. So delta C, okay, I'm going to just do it out. Delta M V equals MV2 minus MV1, because M doesn't change, only V changes. So if you said M1, if you said M2, M1, but M2 equals M1, we have that this expression is just MV2 minus MV1, which is then equal to M delta V. So that is how I moved. I went in the opposite direction. I went from this to this. All right. I want to do some illustrations of these various laws. Newton's first law illustrations. Remember, it says that objects that are traveling with a certain velocity v, both magnitude and direction, will continue to travel with that velocity v. Again, both magnitude and direction, unless acted on by a net external force. So if we have an object at time t1 and it has mass m and it is going in this direction with velocity v, and at time t2 it is going also with that velocity v, then we have that velocity doesn't change, there's no net force. That's what the first law means. That unless acted on by a net force, velocity doesn't change. But let's talk about net forces, because net force doesn't just mean force, it means the sum of forces. Okay, if we have at time t1 and at time t2, we have it going v, and at time t2 we also have it going v, but this time there's forces acting on it. Say F1 in this direction and F2 in this direction, then some of these forces is still zero, because hopefully I've drawn it correctly. F2 is supposed to be the same length as F1. I'll write that out. So its velocity is still the same, even though it had forces acting on it. It's just that the forces canceled out. Now we're going to talk about what it means for to have the net force. If we have at time T1, we have something going with mass m and velocity v. And at that instant, we have two forces acting on it. F1, and this time they are not the same length. Hopefully I've done that justice. We have that the net force let's just do it out. If the net force would be F1 plus F2 plus F2, which is really, I should have set up a coordinate system and showed that these are in the opposite direction, but basically F1 plus F2 is going to have a net force that is more so in this direction. This is going to be the net force. I'll just say the net force is in the green direction because I don't want to confuse you. You can clearly see that F pulls harder than F2. So at a later point in time, T2, the velocity in the initial direction will be bigger. So V2, V1, V2 will be greater than V1. But having a net force can also slow you down. If at time 1 you have mass m and you have this time F1 is smaller than is smaller in magnitude than F2, then the net force will be more towards the opposite direction. And at a later time, T2, we will have a smaller V2. So in this case, V2 will be less than V1. Any questions? Okay, moving on. Let's go to an illustration. If at if we have two masses, m, which is greater than lowercase m, and they both experience the same they both experience the same net force, then one acceleration is going to be smaller than the other. We will have A on the bigger on the bigger mass be smaller. Okay, so since we will have that, oh my goodness. All right. Does anybody have any questions there? All right. Let's move on to the third law, illustration. I guess I'll use orange. When we have, again, when two objects are in contact with each other, they exert forces on each other that are equal in magnitude, but opposite in direction. So I guess we will illustrate that. If we have two masses and they are in contact with each other, then the forces they exert on each other are equal but opposite. And what that means is that, what that really means is that F12 equals and I guess I should have made a note about notation. This means and likewise F12 means the force that one exerts on two. So one thing I emphasize when talking about Newton's third law is in contact with each other. And I'm sure all of you know this, that you have the Earth, you have the moon. They are not physically touching, but they are still exerting a force on each other. And another thing about external forces I want to mention is that you cannot affect your own motion. If I tried to lift myself up to the ceiling by grabbing my belt, I couldn't do it no matter how strong I was. All right, so this is, so far we've talked about acceleration in a linear sense. Everything retained the direction, but acceleration is a vector. And so trajectories can change direction. I want to talk about what's going on here when I say some examples about changing direction. All right. Hey, Elliot, is there some way I can draw a big circle? I mean,
Yes.
is there a tool?
Probably, but
You don't know. Yeah, all right. Cool. I'm going to try to draw a circle the best I can.
I think if you minimize, you get the toolbar, and there's a shape function.
Oh, yeah, probably draw.
Yeah, nice dot shapes.
This is,
I don't know. Let's try.
Get the toolbar.
this is me attempting to draw my best circle.
Okay. Good job. Wow. That's expert.
Dude, that was awesome. All right. Pretty good. All right. I'm going to do 3 different scenarios where a particle is traveling around in a circle, and at different points we know its velocity. We have to find out which direction the force or acceleration is in. If we have 2 velocity vectors. So in the first scenario, we will have V1, and then we will have V2. Okay, and if we do V2 minus V1, this is my attempt to you will have A However, A is towards the center of the circle. If in a different scenario, we had let's see. We had no. How do you, where's the undo? Edit undo. Is that
Control D. It's the back arrow.
all right? Sorry about that. We have V1 here, and we have at another time, we have V2, which is less than V1. If we draw minus V1, we do the operation V2 minus V1. Well, it's supposed to be parallel, but fix this. And we have V2 minus V1. We will have an A that points slightly behind So when a particle is slowing down around the circle, its acceleration is not going to point towards the center of the circle. It's going to point towards the center of the circle and slightly behind. So moving on, you can imagine now that we're going to cover the scenario in which it starts speeding up around a circle. So hopefully this works. Okay, so if we do this minus V1 here, we will have A in this direction, which means that we will be far ahead of the normal. It's not necessarily tangential to the circle. It just happened to be that way. I'll make a note about that. So this is just, I just wanted to show you acceleration does not have to be linear. It does not just have to change the speed. It could also change the direction. Okay, so now we're going to start doing some, scroll up to the circle. Yes, absolutely. And any questions about the circle? All these notes will be uploaded for sure. I'm going to give an example now. It's just this one, these first two examples are sort of trivial algebraic examples, but they start to cultivate some physical intuition. So it's not a bad thing. For example one, I'll just write it out and then read it. All right, let's quickly run through this one. We have that the two forces are equal. And from Newton's second law, we have that they are both equal to m1, mass times acceleration, a1, we have that A2 must be equal to M1A1 divided by M2. So what we have here is the mass of the first box was 1. We said it was given that it experienced an acceleration of 5, and we knew that the mass of the second box was 2. So this is just 5/2, which is 2.5 meters per second squared. So any questions there? Yes, it is 5/2. All right, moving on to another sort of quick example. Yes, that is true. It is 5/11. So let's quickly run through that. We have, again, the two forces are equal. We have mass of the first one was 1. It experienced an acceleration of 5. M2 was, A2 is supposed to be an A2. A2 over an acceleration of 11, which of course, as someone said, it's 5/11, which is equal to 0.45 kilograms. So let's talk about free body diagrams. if we have a tug of war game, we have person one and we have M2, then if we draw all the forces acting on person one, assuming person one is treated as like a point, which is what you will always assume in this class, then the free body diagram will look something like this. We have gravity pointing down, of course, and F grav is obviously minus 9.8 M1 because what the force of gravity is, it's M times the acceleration of gravity. And we will have the tension in the rope, but we will also have the force that the ground exerts on the person. And because the person isn't moving up or down, only side to side, its motion in that direction is 0. So N and F grav must sum to 0. And they're both in the y direction. We have sum of all forces in the y direction equals N1 plus F grav but we also have the forces in the x direction equal T, which also equals M1 times A1 in the x direction. Yeah. So that's the free body diagram for the first person. Now here's the free body diagram for the second person. It is the same and the rope is pulling the other way. It's the same rope. The forces that the T has to be the same because these are two people pulling on each other. They're exerting forces on each other. By Newton's third law, they have to be equal but opposite. So So, it's actually all I have. I thought I had. 1 second. Let's see. This is the only force acting on mass 1. This is the only force acting on mass 1, so, okay. Oh, that's an answer to this. That's an answer to someone else's question, okay. 1 second. Okay, I'm gonna do an example problem and I'm gonna wing it as I go. Let's see. We have a ramp, which is 5 meters tall, and it's inclined at theta equals 30 degrees. And there's this box here. This is, we'll call this M1. And, you know, I want to know, what is the initial speed here is 0. What is the final speed? All right, so the first thing I want to do is find the acceleration of this box. All right, so what do we got here? We have to draw a coordinate system. I'm going to fake extend this ramp and open up some space for a free body diagram. So the force of gravity, as we know, always points down. Okay? The normal force doesn't always point up. It always points at a right angle to the surface. That's a nuance. And there's reasons for that, which are pretty cool, but we won't get into it. it's really a manifestation of Newton's third law with the ramp and the ground. I said the word manifestation. So one thing we need to do is lay down a coordinate system. I'm going to lay down a coordinate system such that this is the x direction and this is the y direction. So this may be really odd to you that x is not always completely horizontal and y is not completely vertical. But it is always a strategy in physics to simplify the motion down to the parameters which describe it. So that's a strategy you're going to have to learn, but I'm going to proceed with it. We have to decompose this gravity into the y direction. Again, the y direction doesn't have to be completely down. So we have a force pointing in the direction of the ramp, of the slant ramp. That's the x component of the gravity force. And it's going to be, this one's going to be m1g. This is going to be all right, a quick trigonometry thing right here. If this angle is theta, then I'm going to show that this angle is also theta. Okay, we extend this line, and this is going to be a perpendicular. If this is theta, then this right here would be 90 minus theta. This would have to be 90. This, of course, would have to be 90. So this theta would have to be theta. So theta. Okay, let's. The point is that the angle right here is theta. Yeah, but this problem is frictionless. Yes, forgot to mention that. Okay, so what's going to happen is we have summation of the forces in the x direction are going to be m1g sine theta and m1g cosine theta. Equals g cosine theta I will not forget to send you the notes. I made a mistake there. Because it's not moving off the platform. It's not moving off the surface of the ramp. There's no motion in that direction. Okay, so, and this would be equal to m1 a x. Again, x is along the direction of the ramp. So we need to solve for ax. Ax will, well, the m1s cancel. So ax will just be equal to g sine theta, and theta equals 30, right? Sine of 30 is 1/2. Sine of 30 is 1/2, yes. So this would be 9.8 over 2, which is 4.9. And so there we go. There, you want to know what the final speed it is when it hits the ground. If you recall, we have this formula from the first day of class, maybe it was the second day, plus 2a delta x. Well, we have VIX. It started at 0. We now have A, which is 4.9. So what we need to do now is find the length that it travels to reach the bottom. The length that it travels to reach the bottom. If this is 5, this is 30, sine of 30 is 1/2, so that has to be 10. This has to be 5 and 3. You will see that delta x has to equal 10. So what we have here is VFX squared equals 0 squared plus 2 times 4.9 times 10. So what we need to do now is just take the square root of both sides. And the final speed when it hits the ground is VF equals root 98. That's somewhere between 9 and 10. Yes, 10 is how much it must travel. Route 98 is the speed it will have when it hits the ground on the ramp. That's all I have for today. We're pretty close to the end. Maybe quickly I can answer questions. I will definitely send the notes. I mean, I think they assume you know how to do it. It's expected of you. It's looked down upon not to simplify it, but nobody's going to be that pedantic. I don't.
Actually, in physics, they'll probably take a decimal answer because
Oh yeah, that is true in physics because
it's not bad.
things have units, and they're usually physical problems have decimal lengths. You know, yeah, okay, I see what Elliot's saying. So, yes, the M1G cosine theta does cancel it out, yes. Well, that's all I have. We've saved the notes. They will be sent. I'll stay on the line. Until we get it uploaded. But that's all I have for today. Thank you. Hold on. Yeah. Okay. The notes will be uploaded soon.